Okay, in this problem, we're going to solve sentiment analysis. Our task is actually to code up a neural network that can recognize positive or negative emotion in an input sentence. And we are going to code up a neural network, so I'll assume that you're familiar with the idea of a neural network. We want to be able to feed in a sentence like, the movie was okay. The movie was okay. So the input to this model is going to be some kind of sentence. It could be just one sentence, it could be multiple sentences, but we know that it will be a string. The movie was okay. And it says that we actually want the model's prediction to be a number between 0 and 1. So for something like the movie was okay, maybe it would output something like 0.5 or maybe 0.4 because it's slightly more on the negative side. But we want to build a model that can actually detect and assess the emotion within an input sentence. And the problem says that this is actually an application of word embeddings. So by this point, we're familiar with the idea of neural networks. We have nodes, and these nodes are connected in a way that we have a bunch of numbers being multiplied with each other. And each of these can be thought of as a layer, this one being the input layer, and the second one being, say, a hidden layer. And it turns out in ChatGPT's neural network, which we're going to work up to coding up, the first layer is actually called an embedding layer. And embeddings are actually the core concept within this problem. One of the main benefits of this problem is that it teaches us how to actually use word embeddings within a neural network. So let's get into it. I would highly recommend checking out the detailed background video on word embeddings, but if you need a refresher, we're also going to explain it in this video. So the problem tells us the model architecture to use. That's over here. And that's what actually is going to be defined in the constructor. And then we go ahead and actually have to code up the forward method, which will return the model's prediction for some sort of input sentence. And we'll come back to the model architecture later, but this is essentially explaining the parts of the layers of the neural network that we're going to use. And we are told that we have to code up both the constructor and the forward method within this class, and we do not want to actually train the model. We do not want to code up the gradient descent loop. So what does the model actually take in as input? We're going to take in vocabulary size. Vocabulary size is going to be an integer that represents the number of different words that the model should be able to recognize. And of course, we're going to explain embeddings in a bit more detail in a bit, but if you're familiar with word embeddings, we know that embeddings are actually just a lookup table. For every possible word or token in our vocabulary, we want to be able to fetch or query the embedding vector. That is actually a learned and trained embedding vector. It consists of weights that is learned through gradient descent, but regardless of how we look at it, there is some fixed set of words the model should be able to recognize, and that is essentially the number of rows in this lookup table. And of course, we are also given a list of strings x, each with negative emotion. So let's go ahead and take a look at those actual examples, the vocab size, and x, the list of strings. So if we go ahead and take a look at these inputs, we can see that vocabulary size here is just a number 170,000. And this might seem a bit weird, but remember that vocabulary size is not the number of unique words in your actual input sentences. And we'll describe what these numbers are in a second. Vocabulary size is just the number of words that your model should be able to recognize. So this is actually the number of words in the English language, but we might actually have a very small subset of words in the list of strings that we want to get the model's prediction for the emotion for. So it is highly recommended that you have solved the problem NLP intro before solving this problem, but if you haven't, it's okay. Essentially what that problem teaches us is that after we decide on our tokenizer, and our tokenizer in NLP is just how are we going to split up the words in a sentence. Let's say for simplicity, we're going to split up the sentence based on spaces. So we break it up into individual words and feed in a list of words into the model. But after we've done our tokenization, we actually have to convert each word, each string, to some sort of number, right? These neural networks, these models, they only understand numbers to actually do all the matrix multiplications that make up a neural network, as well as calculate all the derivatives needed to optimize the model. The model has to be dealing with numbers as input, specifically just vectors and matrices of numbers. So for every single token, for every single word, for the, then for movie, then for was, then for okay, we actually need to assign a consistent mapping between numbers and these strings. And I've gone ahead and went and already done that as I created the test cases for this problem. So let's go ahead and assume that this first sentence that is passed in is the movie was okay, right? Slightly negative, slightly neutral sentence. And that's actually what's represented in here as the first list within X. The movie was okay. And because we don't want this to be like a jagged tensor, we want this to actually be rectangular, and we want the number of columns in the first row to match the number of columns in the second row. Again, we'll get to that second sentence in a bit, but you can actually see that after the word okay, which is represented over here, we have just kind of padded the rest of this row with zeros. And the model will learn to just kind of ignore the zeros, as we'll explain later. And then for the second sentence, we go ahead and have, I don't think anyone should ever waste their money on this movie. This one is again split up word by word, with each string encoded as a number, and that is actually the second row within X represented over here. And if you check the mappings between the strings and the numbers, you'll find that it is consistent. And we can see that for the first string within X, the first example, the model is supposed to output something like 0.5, because that's kind of a neutral sentence. We could say it's a bit negative, so maybe 0.4, but 0.5 does encapsulate how neutral that sentence is. But this second sentence, right, this one over here, the second row in X, this is a strongly negative sentence. And we said that 0 was the most negative a sentence would be. Maybe that would be like, I hated that movie, it was utter garbage. Maybe that would be like very close to 0. But we'll go ahead and say that the model should output 0.1, something really close to 0, definitely far away from 1 for that second example. So this is essentially the output. This is the output for the forward method. And vocabulary size is something that the constructor receives, as that's just like kind of an attribute of the neural network. And also just want to clarify that the output of, say, 0.5 and 0.1, that's just to help you actually understand the shape of the inputs and outputs. If you actually print your model prediction after you're done solving this problem and you train and you submit the code, it won't exactly match these numbers because we won't be training the model. So the model's prediction as it is, before you do any training, when you have this random initialization of the weights and numbers inside the neural network, you won't get these like really nice predictions that actually detect the emotion. To do that, you actually have to do a training loop. There is a separate problem for that in this playlist. You actually have to write the training loop, but don't worry, there's actually a Google Colab, which is just a notebook of Python code that you can click run on each cell and see the output. There is a Colab notebook linked in the description for this problem, and that will actually use the exact code that you write for this problem. There's no more code you have to write after you get your accepted solution on this platform. And once you solve the problem, you'll be able to actually see the model being trained on Colab. I have comments and text blocks explaining what each cell is doing, and you'll be able to see the model actually achieve this performance. Actually, we have some even more interesting examples to see that the model can learn to generate emotion. And we're going to use your code, your solution code exactly in this Colab notebook. So definitely don't check out the Colab notebook until you solve the problem. Now let's explain the model architecture. So if the input into our model is b by t, where t is the number of words in each sentence, then the first step should actually be for every single token, for every single word at each time step t, we want to actually get the embedding vector for that word or for that token. And just kind of a crash course on what embedding vectors are. It's essentially the model learning to represent the meaning of a word or a character, in this case words, in numbers. And once we're actually done training the model, these embeddings will actually make sense. So let's say our embedding dimension was 2. For every single word, we were going to learn a vector of size 2. There would be 2 entries in this vector, and these numerical vectors are supposed to encapsulate the meaning of the word. Then what we would find after we're done training and we have learned the right representations for each word is similar words when you graph them. Let's assume that it's actually a dimension we can graph. Obviously, in the problem, we're going to use dimension 16, which is not graphable, but let's assume it was just 2-dimensional, a dimension we can graph. Then what you'll actually find is similar words will actually be plotted next to each other once that training process is done. So you might have like man over here, and you might have like women over here, because obviously these words are related in the English language and they have some similarities in their meaning, but there is obviously a slight difference that we can tell between them. These vectors are not entirely on top of each other. So when we say we want to use an embedding layer of size 16, it actually means that in the constructor for this model, we need to define that lookup table that's eventually going to be trained. And the number of rows in that table should just be the vocabulary size, right? For every single token in a word in our vocabulary, we need to learn that embedding table. And it should be vocabulary size by whatever our embedding dimension is. And that's just kind of a parameter that's up to us as the designers of the neural network to choose. As we choose higher and higher numbers for this, in this case, you can see that 2 is the embedding dimension, but as we choose higher and higher numbers, 16, 32, 64, 128, and so on, the model learns a more and more complex representation and can understand language at a deeper level. So in this case, as we instantiate our embedding layer, we're actually just going to use nn.embedding in our constructor, and we'll just pass in the vocabulary size as well as the embedding dimension, which is 16. And in the forward method for our model, we'll just call the forward method for this instance of nn.embedding, and that will actually get us the embeddings for every token. The output of that would be b by t by, let's call that b by t by e, where e is the embedding dimension, because for every single token, we would have the embedding dimension. So that would actually be the first line of code in the constructor, just declaring this nn.embedding instance where v is the vocabulary size, as well as the first line in the forward method where we want to call the forward method of the embedding layer and get our b by t by e tensor. However, for these series of vectors that we have for the entire sentence, for each sentence, which is of length t, we have a bunch of vectors, and each of those vectors are of size e. We need some way to kind of combine or aggregate this information into a single vector to kind of have the model take into account all the information for a sentence across every single word. We want to kind of combine that. And the way we're going to do that is we're just going to average all the embeddings for across all the time steps for each example across the batch dimension. So to make that super clear, we want to take our b by t by e tensor and end up with a b by e tensor. And you can think of that as for every single batch element, we actually have a t by e tensor, t rows and e columns. And what you actually want to do is you actually want to compute the average of every single row here, because every single row is actually a time step where the number of columns in every row is e. But we want to end up with one single vector of size e. So just to make that super clear, we actually have t rows and we have e columns. So you want to take this row, this row, this row. You want to take all the rows and average them together until you end up with essentially one horizontal vector of size e. And then for every single batch element, for each independent sentence or string that's passed into this model that the model needs to get the emotion of, then we will actually have one vector of size e encapsulating that sentence and its meaning. And that's going to then be used for the final layer of the model, which we'll get to in a bit. It will be a linear layer. That will be used as input to the final linear layer, which should then get us a single number for every single element across the batch dimension. And in code, how we would do that in the forward method is we would take embedded, which is b by t by e, pass it into torch.mean, and say dim equals 1, because that's the dimension we want to collapse out. We want to collapse out this dimension and end up with something that is b by e. And this averaging is actually called the bag of words model in NLP. And the reason it's called that is you can think of taking all these vectors for every single word in a sentence, and you're just jumbling them all up together. You're just mixing them all up. You're just averaging them in a single bag, so to speak. You're not really worrying about the fact that one word comes after another in the sentence. You're not worrying about the sequential order of the words in the sentence. You're just taking all of them and you're going to average their embedding vectors into a single bag, and that's why we call it the bag of words. So the next part in the neural network is to take these 16 neurons, right? Because we know that once we have our b by 16, our b by e tensor, we know that for every batch element, remember we look at those independently in parallel, for every batch element, there are 16 numbers, right? We have a feature vector of size 16, and we want to actually then collapse that into a single number. We want one number that encapsulates the output for the model's prediction for that example. So this is one neuron, this is just one number. And we know that this neuron, if you're familiar with linear regression, should have W1 all the way through W16, and of course that optional constant term or bias, B. And this linear layer is then going to learn the values of W1 through W16, as well as that optional constant term, B, the bias. such that we can, minimize the error and the model actually has the right valid prediction for this one number. However, this number is not guaranteed to be between 0 and 1 as we actually desired, right? That number is just some number. It could have some number of decimal places, could be negative, could be positive. It doesn't have any restrictions. It could be greater than 0, greater than 1, could be like negative 5,000, could be anything, right? And we want to squash the model's predictions to be in the range of 0 and 1. And that's where the sigmoid function, which we actually use in previous problems like the handwritten digit classification problem, that's where the sigmoid layer actually becomes very useful. So we will toss an nn.sigmoid call. We'll actually define this in the constructor, and then you can go ahead and call the forward method of nn.sigmoid in the forward method for this problem. We will toss a sigmoid layer at the end such that we end up with, as we wanted, that b by e tensor, but then all our numbers, we'll end up with error b by 1 tensor, but all those numbers will be between 0 and 1. Okay, now let's jump into the code. We know the first thing that we need to declare in the constructor is actually the embedding layer. That's the first layer of the neural network. So we can go ahead and say self.embedding layer equals nn.embedding, and first thing that nn.embedding requires us to pass in is the number of rows of this trainable table, which is actually going to be vocabulary size, and the size of the vector will go ahead and be 16. And that's the size of each trainable feature vector for each word. And the next layer that we need, well, first we're going to do the averaging, but that would occur in the forward method. So the next layer we actually need here, the next trainable layer, is going to be the linear layer. So we'll say self.linear equals nn.linear, and we know the input number of neurons is 16, and the output number of neurons is just 1. And of course we need our sigmoid layer, so we can say nn.sigmoid, and that's it for the constructor. Next, we can move on to writing the forward method, also known as getModelPrediction. We know we need the embedded version of the input. So that would be self.embedding layer of x. That's just calling the forward method from this embedding layer module. It itself is a subclass of nn.module, meaning that it is a neural network model, or at least we can think of it as a trainable layer, which would make up a neural network model. And then we can go ahead and average, right? So because we want to get the b by embed dim tensor, just as the comment says over here. So that would be, we could say averaged equals torch.mean of embedded. And again, we want to, it's b by t by embed dim. We want to squeeze out the t. So we can say dim equals not 0, not 2, but 1. And we also want to pass this into the linear layer. So we would go ahead and say something like projected. And the reason this makes sense is you're kind of like projecting this vector of size 16 down into a single number. So you can go ahead and say self.linear of averaged. And lastly, of course, we know we need to get these between 0 and 1 to interpret them as emotion, right? 0 being completely negative and 1 being completely positive. So that would go ahead and be like predictions equals self.sigmoid of projected. And this is what we actually want to return. We just need to round our answer to 4 decimal places. So let's return torch.round of predictions and say decimals equals 4. And we're done. And we can see that the code works. Embeddings are a super important concept in natural language processing, and they're actually the first layer in the neural network for ChatGPT. I definitely recommend understanding the code for this problem as well as the concepts behind it super well. And if you need to, you can refer back to the background video that's linked in the description. That's just kind of a whiteboarding video where I explain embeddings in more detail. And now that we've solved this problem, the next problems to jump into, kind of part 2 in this series of problems, are all going to be building us up towards coding ChatGPT, building in the dataset to train a ChatGPT replica, as well as coding up the neural network layers themselves. So hopefully I'll see you soon.